I can hear myself, but now? You can hear me now? All right. Well, it's my pleasure to introduce our speaker for today's seminar. It's Professor John Shen. He comes from Illinois Institute of Technology, where he is the Granger Endowed Chair Professor. Here at Illinois, we know what Granger is, so I don't think we need to explain as a very, very nice position, right? Let me give you a brief biography of John. He received his BS from Tsinghua University in China in 1987. He received the MS and PhD degrees in electrical engineering from Rensselaer Polytechnic Institute in 1991 and 1994 respectively. Then he held various positions, including senior principal staff engineer with Motorola Power Products Division between 1995 and 1999. And then he was on the faculty of the University of Michigan Dearborn between 1999 and 2004. And then he moved down to the University of Central Florida, where he was until 2012. And then recently he joined Illinois Institute of Technology in 2013 as the Granger Endowed Chair Professor in the Department of Electrical and Computer Engineering. He's also served as the Chief Scientist and a board member of Great Wall Semiconductor between 2002 and 2012. And I was telling John earlier today that I had experience with that company back in graduate school. They were sort of one of the first to talk about lateral power devices. So really lower voltage, really high frequency. I was a high frequency guy. So that's sort of in that space, very well received products that are still in a lot of products today, being used in IBM, for instance, many of their server applications. He's got a ton of awards. You saw the bio itself, so I can't talk about them all, but he's got 2 IEEE Intersections Prize Paper Awards and the NSF Career Award, amongst very many other things. He's been very active in the Pell Society, and he actually comes and brings us a gift to the student chapter. Do we have a chapter president? Okay, I'll let you give the gift to our chapter president.
Each chapter should have one of those banners from a Power Electronics Society when you have a chapter activity, chapter events. So, anybody taking a picture? No. Well, so here you go.
Okay. So, so without further ado, let's welcome our speaker and thank our speaker.
Thank you. Well, thank you, Robert. Thank you for coming here. This seminar is just about the past, the present, and the future of IGBT technology. I'm pretty sure everyone sitting here knows what IGBT is for, right? It's standing for the insulated gate bipolar transistor. It's arguably the most important power switch in the medium power market right now. It's not just for the big factory, power system, hybrid electrical vehicle, big motor drive. Actually, every one of us in this room, we own a few of those IGBTs. You probably don't believe me, but let me pass those. Phil found, Professor Crane found from his lab. There are IGBT chips. There are 2 IGBT chips and 2 diode chips. I'll pass those along. But the ones you have in your personal possession, you drive a car, right? Most of us drive a car. In each car, they are internal combustion engine. There are different cylinders. When you try to fire each cylinder, you need one IGBT to do that. So each of us own at least 4 IGBT, or if not 8 or 16. Okay. And for those you don't drive, you still own some IGBTs. The little smartphone you have with a flash for the camera, the flash is controlled by a small IGBT to release the large current to discharge a capacitor, basically. So we all own 1 or more IGBTs. Okay. Let's talk a little bit about the application and market of power semiconductor devices in general. Basically, you have many different kind of power devices, not just IGBT. You have a power MOSFET. You have the good old bipolar junction transistor. You have the really good old thyristors, SAR, GTOs, those devices. They are all good for certain range of power ratings and the switching frequency ratings. As you can see, the frequency range here and the power ratings here. IGBT fits nicely in the medium power and the medium frequency range. Of course, you want to drive the converters a little bit faster, like a rubber does. You have to push it out with the wide bandgap semiconductor devices. How big is the power semiconductor market? The industry produces roughly about $15 to $16 billion worth of power MOSFET, IGBTs, even the good old diodes. You can see the roughly the overall market is about $30 billion, but you cut that into half. Half the PWM, power management ICs. The other half discrete devices. Within discrete devices, about half that are low voltage power MOSFET. The 20, 30 volts MOSFET we use in the server power architectures, the laptop computer motherboard power supplies, they're in this domain. But the second place is taken by IGBT. This is the old number. Right now, the IGBT market revenue is probably between $3 to $3.5 billion. Okay. And if you look at where we're using those power semiconductor devices, we are actually, let's look at a little bit of future number here. This part is ICT sector, the information communication sector. And this is the consumer sector, include our cell phones, our tablets, our PCs. And this green is industrial, including utility power, the smart grid application, while the top one is the automobile, including the hybrid and the plug-in electrical vehicles. Now let's talk about IGBT a little bit. We all understand, I hope you all heard about how IGBT operates. It's really a combinational device. The major power switching part is a bipolar transistor with its gate current supplied by a power MOSFET. So you have this BJT and MOSFET Darlington configuration. IGBT was invented back into the late 70s, early 80s. Around that time, people I'm actually not old enough to to remember those things. Around that time, if you design a high power converter, you have two choices. Okay, you have the bipolar transistor at that time can handle hundreds of amps, 600 volts, 1200 volts, and you could have a power MOSFET, but power MOSFET handles much lower current. The problem with the power BJTs they are current control devices, and they have a very low current gain. The beta is very low, typically down to the single digit. So to switch 100 amps current, you need at least 10 amps as the controlling current. So you need another power supply to do the control. It's not very efficient. It's very hard to facilitate, to implement the control. On the other hand, the power MOSFET is a great devices. They just came up to the market. Phil, you remember this in the 1984, 85 kind of a time frame, 82? I'm sorry, 70, 76, 77. Yeah, later 70s. Great devices. You just use a voltage to control that. You could actually use a simple microcontroller to drive the power MOSFET directly if you don't care about the switching time. Just a few milliamps, you can turn them on and off. Very slow though. So naturally, people would think, what if I combine those two devices and make that a voltage controlled, but nevertheless still a bipolar type of devices that can handle a large amount of current? Okay, several groups came up to the same idea around the same time, almost the same time. And notably, Professor Jay Bolliger from North Carolina State University, he was at GE at that time. And a research group from RCA, And also, of course, Professor Jim Plummer from Stanford University. There are quite a few others also reached the same conclusion around the same time. So the true inventorship of the IGBT technology, I'm not going to make any comment about that. It's very subject to open debate. The funny thing is, a few years ago, people realized a young engineer from Mitsubishi actually filed a Japanese patent back in 1967. Nobody knew about that until just a few years ago. So they didn't mention the word IGBT. They did not mention the application into the power world, but that device structure is exactly what we have today. And even Mitsubishi didn't know that. They had to pay a lot of money to General Electric to license that technology for 20 years. So it tells you how you find those funny stories in the technology history now. So it first came out the idea, and everybody jumped onto that. The Japanese companies, the US companies, everyone jumped onto that. Initially, people call those IGBTs punch-through IGBT. When you read those old literature, you still come across the word punch-through. Basically, those IGBTs are made on a thin layer of epitaxial wafers. Okay. Because you have a relatively thin epitaxial layers, when the device blocks voltage in the off state, the depletion region push all the way through to the substrate. And that's everybody's common approach, with one exception. Siemens, now they're called Infineon now. The Siemens Semiconductor, before they got spun off as Infineon. They realized this epitaxial wafers are super expensive compared to wafers in a single crystal without epitaxial. They call those flow zone wafers. So the only motivation driving them down a different road is the cost of wafers. So they were the only one who did not use the punch-through structure. They use a non-punch-through structure where you have a fairly thick epi, 400-500 microns epi thickness. I'm sorry, it's not epi, the wafer thickness, versus 50 micron to 100 microns epi thickness. But later on, people realized, and those MPT device structures gives you more advantage in terms of the device reliability and the toughness. We call those the ruggedness of the device. They can handle a whole lot more abuse from a voltage and current pulses. Okay, and everybody switched to this MPT philosophy at the end of the 1990s. The funny thing is, today, if you go buy wafers, because of the market dynamics, the epi wafers actually cost less than the flow zone wafers. So the original motivation for the Siemens getting into this technology directions is totally out of the window. But nevertheless, they came up with a device. People got the unexpected benefit from that technology solution. So the moral of the story is, well, we can lay out the roadmap, we do the right thing, but at the end, you may get those side benefit you never expected. It's like a Forrest Gump movie, right? Life is like a box of chocolate. You won't know what you're getting. So it happens quite often in this field. I think in other fields too. And moving into the 2000s, this decade is all about the trench IGBT. Instead of making the planar structures, people around that time, people realized in the low voltage power MOSFET, people introduced a lot of those fine-scaled device structure made in the trench. People borrowed the trench structure from the DRAM. In all the DRAM chips, we tend to dig a skinny, small trench to make capacitors to store the ones and the zeros, right? So once they have their processing technology, people start borrowing those into the power device area. In the beginning, the belief is always, well, make the cell structure so small, we have a high cell density, so we can reduce the forward conduction voltage. Yes, it did. It did help, and the people actually got more than they expected. People realized, according to our expectation or our calculation, we're supposed to get, let's say 20% improvement. They ended up with a 50% improvement. Okay. Again, same thing happened. There are unexpected a good result come out of some research idea. Okay. We can talk about that a little bit later. So moving into the future, this is almost 30-some years now. This technology is pretty old compared to this newer things, wide bandgap semiconductor, silicon carbide, gallium nitride. Silicon IGBT is a pretty old technology, pretty mature technology now. Looking in the future, is there anything new we can do to further improve the performance? The answer is yes. There are a few examples later on we're going to examine. One is what I call the nano IGBTs. And the other one, of course, is the silicon carbide IGBTs. And the third one is I'm working on personally is a wafer-scaled IGBT. We try to make IGBT to carry out thousands of amps instead of just maybe 100 or 200 amps.
Can you tell us about amperage went up in the same time period we were discussing there?
Yes. In the early 80s, each device is probably about 10, 20 amps. People selling you those things. They're still selling those 10, 20 amp devices in discrete form. Moving into 1990s, along the same time window, I'm glad you asked the question. I left out some of the subject here. People developed this power module thing, which is the one thing I borrowed from Phil's lab. This is power module where you can put a relatively large IGBT die in parallel to carry current in the amount of a couple hundred amps. So after the power module technology is introduced, 100 amps, 200 amps, sometimes even 500, 600 amps is it become a reality. So that trend goes all the way to today. So we have IGBT modules, not a single die, but modules with a current rating in the couple hundred amps rating, and with a voltage rating of early days 600 volts to begin with. Now we have 1200 volts. 1700 volts, 2500 volts, 3300 volts, 4500 volts. The highest power rating for silicon IGBT is 6500 volts. And we used those 6500 volts devices in very high power applications such as high voltage HVDC light, the voltage source based HVDC light. We're talking about a couple hundreds of megawatts and 200-300 kilovolts, very high voltage, but you need a different topology to stack up a lot of IGBTs to handle that kind of voltage range. Did I answer your question? Yeah.
No charge for the question.
We planned that question actually. Well, when you look at the IGBT from a device technology's point of view, there's three things we look at. The first thing is what people call VC-on, the forward conduction voltage drop. And the second one is this turn off switching and power loss. And I know you already know this. Why we only talk about turn off? You don't talk about the turn on switching loss for IGBT. Anyone? In the go ahead.
Because presence of tail current in the IGBT, that there is you need to compute the current takes longer time to decay down, and so.
That's why you need to talk about turn off. Yes, but why we are not including the whole turn on and turn off components? Make it a total switching loss. The reason for that is we always have this IGBT working together with anti-parallel freewheeling diode, right? The turn-off loss for IGBT, as you can see from the waveform, it has this long tail, as you pointed out. It's determined by the IGBT itself, but the turn-on loss for IGBT is determined by its companion freewheeling diode, the reverse recovery of your freewheeling diode, not by the IGBT, mostly. Okay, that's why when people give you the performance of the IGBT, they only talk about the turn off performance. They do not talk about the turn on because that's somebody else's device. That's the diode performance. Okay. If you look at the manufacturer's data sheet those days, there are not too many IGBT manufacturers available today. I counted probably less than 10. In the early days, everybody is doing IGBT, but now it kind of consolidated. If you look at the data sheet, they're more or less about the same in terms of the VCE and the turn-off energy loss. What different among different manufacturers is the third leg of this whole picture. Some other tangible factors, for example, the short circuit capability, the EMI, the dynamic breakdown, the temperature coefficient. Those things, when you design your converters, you do not normally consider those for the first round design consideration. You really look at those two things. Okay, but at the end, what differentiates a good, a superior product from an okay product is really in this domain. And this is I wouldn't call them intangible. They're tangible, but nevertheless, second order effects. Okay. Started from the middle 1990s, 1995, 1996. People spend a lot of time to improve the conductivity modulation of IGBT. IGBT is a bipolar device where you use both electron and holes and mix the two up and having a lot of them because you have so many free moving charge carriers. That's how IGBT carry a large amount of current. Okay, you could have an electron hole concentration a few orders of magnitude higher than the background doping. That process is called conductivity modulation. Okay, in the early days, the IGBT having this kind of conductivity modulation profile. This is basically the concentration of electron holes. Okay, along the vertical direction of the IGBT. So you typically have IGBT is well conductivity modulated as a backhand, but near the top surface, because that's where you have the MOS channel, the conductivity modulation is not so good. If you compare the most ideal conductivity modulated device, if you take a device class, people will tell you a PN diode, a PRN diode is the closest thing to an ideal conductivity modulation. You basically inject electron from one end, you inject the holes from the other end, you mix the two in the middle, you flood this entire lightly doped region with the electron holes. You need that lightly doped region to block the very high voltage when the device is in the off state. But when it's in the on state, you need to flood it with a lot of electron holes. So the effort in the IGBT world for the last 15 years is how do we make the IGBT more like this? Okay, people actually did that, and almost accidentally. Remember we were talking. People introduced the trench technology. So this is the gate, polysilicon gate inside the trench. They thought using the trench can only increase the cell density. So you get the 20% reduction on the VCE. They ended up with 50% reduction. They didn't realize by introducing the trench structure, we actually changed the electron hole profile into this kind of shape, which is very close to that of the PIN diode. Okay, this is almost after the fact. After the people carried out the experiment, they realized the good result. They went back to trying to find out what worked so great. It's not what went wrong, but what went so right. They realized this, and this is some of the device structures to realize that you could use the trench, but you could also use the planar structure, but by adding some N regions to prevent the holes injected from the bottom, but they tend to be absorbed by the P region. That's the collector of the PNP transistor. They do not want the P region to collect all the electrons so quickly. They want the holes to hang out in this general area to mix up with the electrons to sustain the high conductivity level. Okay, I'm not going to get into the details of those device structures. This came from a paper published 8 years ago by a gentleman from ABB Semiconductor. This is essentially seeing the same thing. This is a traditional structure. We have a profile like this, but if we move that into a trench structure, we end up with a carrier profile more like a rectangular shape, much, much more ideal. And the other trend in the industry is, in the early days, we talk about the punch-through structure. You can see there's a thin epi, and the Infineon, Siemens people, they use a very long wafer. But if you can combine the two into today's flow zone wafer, but we grind the flow zone wafer so thin, you get the best of the both worlds. That's pretty much everybody's technology right now. You heard the word field stopped IGBT, ST field stopped field FS IGBT. This is what it is. In the old days, back in 1995, we have flow zone IGBT with a 300 micron in thickness. And gradually over the years, you can see right now it's only 100 micron thick. And if the thickness go down to 60 microns, the silicon wafer won't be rigid anymore. It's pretty much like a taco. You can kind of roll it, putting some all the goody stuff on top. Okay. Also, the trick is how to grind the wafer so thin, and you can still continue processing it without breaking the wafer. Okay, that nobody talk about that. It's industrial secret. Everybody has their own secret. There's no publication on that. And it's hard to compare the IGBT performance among different vendors because they all try to show you the best number under the specific testing condition. So over the years, I was able to collect all those data and kind of normalize them into this so-called specific RDS-on. So this way you're not compare a small die with a very large die. That's not an apple-to-apple comparison. But we also specify the IGBT has to be measured at 125 degrees C. They have to have the same switching performance because different manufacturers, they have a slow IGBT, which has a great conduction capability, but they're not so good at the fast switching. So over the years, you can see it came all the way down from 80 milliohm centimeter all the way down into maybe a single digit now. Okay. So those are the companies that are still in business with a single exception of GE. They're not in that IGBT business anymore. Everyone else, they're still in the IGBT business. Okay, let's talk about the high power IGBT, very high power IGBT. The IGBT voltage rating, as I pointed out, is ranging from 600 volts to 6,500 volts, with the current rating maybe 100 amps to a couple hundred amps. Usually, they're used in the power application between maybe 1 kilowatts to a couple hundred kilowatts. Okay, for example, an electrical vehicle right now, a Prius. I know, Phil, you're driving a Prius. It's what, 55 kilowatts. Okay, so you upgraded. But for the very high power applications, 5 megawatts, 10 megawatts, people still use, at least until a couple of years ago, people still use the thyristors or SARs, or GTOs, or IGCTs. The newer version of that. But the general trend is to replace those slow switching, hard to drive devices with IGBTs. This is from a paper from Tamic, a Japanese company, I think a joint venture between Toshiba and Mitsubishi. They are in this high power converter domain. This is a new steel mill converters, typically 5 megawatts. And then you can see from 1999, they're still using the cyclone converter and DC choppers, and moving into the newer 1990s, they're doing more IGCT, GTO kind of drive, the blue bars. And entering 2003, 2004, it's pretty much all IGT, which is another, a brand name for IGBT. It's essentially the same thing from Toshiba. So IGBT is getting into this megawatts drive range now. And if you look at the future applications, especially the high voltage DC light, all kind of flexible AC transmission devices, IGBT is gaining traction in those areas. Not as a traditional application area, but they're getting into that. And this is the kind of multi-level cascaded converter topologies people use to handle hundreds of kilowatts with only 6,500 volts IGBTs. How do you handle 100 kilovolts? You just put a whole bunch of them into the different kind of circuit topology. Altogether, they support this high voltage. Yeah. Now, it would be awfully nice not to have an IGBT device that can handle 6,500 volts and maybe 4,000 amps. One single module, one single device. Mainly to drive the IGBT from this medium power, medium frequency range into the high power, but maybe still a low frequency range, because at a couple of megawatts, people do not tend to switch those that fast. For one thing, the switching loss will be high. For the other thing, there's not a whole lot of need to switch it so fast. Especially when you use multi-level converters, the equivalent output frequency will be always higher than the individual stages of switching frequencies. For each individual switching stage, maybe 1 kilohertz, maybe 500 hertz is all you need. But the beauty of using IGBT instead of GTO is, some paper they did a comparison between GTO and IGBT in the high power applications. Basically, the conduction loss, the switching loss is about the same. Okay, but to use IGBT, you do not need a snubber. Okay, while GTOs need a big, heavy snubbers, the snubber dissipates a whole lot more additional power, and it takes a lot of space and weight in the system. It's not easy to control either. So there is some advantage to drive this IGBT into this high power, low frequency domain. Typically what we do is, with those IGBT modules, is we have multiple die. We have an IGBT wafer. It's made of a couple hundred identical IGBT die. We pick the good die, put them in parallel in the module. Each die is less than 2 centimeters square. If you make them too big, they're very sensitive to the defect. You ended up with a very low yield from the wafer fabrication. But if you compare how people make thyristors, we make the entire wafer as a one thyristor device. That's how thyristors can carry 5,000 to 6,000 amps for each of those hockey puck kind of package. Well, you may ask, would the thyristor wafers be also sensitive to the defects? Well, not as much, because the thyristor cell structure, they have a much larger dimension, and they have much deeper junction depths. They're at least 1 order of magnitude larger than the IGBT. So they are not as sensitive to those crystal defects on the wafer. So the question is, this is some idea we've been trying to drive in the last 2 years, is can we make IGBT also use the entire wafer? We call it wafer scale with IGBT. Okay, And by dividing the IGBT into multiple segments, you know some segment will not work because of the sensitivity to the defect. But at the end of the IGBT fabrication process, can you single it out? Could you sort it out those defective zones and use some kind of redundancy manufacturing technology to electrically isolate them out, but physically we don't have to remove them? Okay, if that's being the case, we can package the IGBT into the same hockey puck packaging with two huge copper sandwiches of wafer together, so you can get the main current out without all this. We're passing this around. There's bound wires, thin bound wires with a lot of inductance, a lot of parasitics, and there are also the unmatched characteristic among those chips in the same module. The chips on the zones on the same IGBT wafer, they match much better. So we've been doing this research. We are a little bit successful, but we still got a long way to go to realize this concept. So looking into the future, how much time do I have? I got another 10 minutes maybe. Looking into the future, are we at the end of the IGBT, silicon IGBT technology? Well, this is the silicon theoretical limit, this line here. And the blue dot here are the silicon superjunction power MOSFET, like the CoolMOS from Infineon. And the silicon IGBT performance are right here. And back into 2006, Dr. Nakagawa from Toshiba, he did some theoretical study. He tried to shrink the cell structure of the IGBT from a few micrometers into just a couple hundred nanometers range. The structure looked exactly the same, except the dimension got shrunk by 10 times. And he realized you can actually carry out a whole lot more current when you do that. Actually, you can carry out the theoretical limit right here. That's 5 times more current than the IGBT product on the market today. If you can fabricate the IGBT device into the nanometer, it's not even a nanometer, it's a couple hundred nanometer range. Okay. The reason for that is when you shrink the device into such a skinny pillar structure, the built-in depletion region will pinch off this access for the host to the P region. So the host has no place to turn to. When they're just about ready to be collected by the P region here, they can't overcome the barrier formed by the depletion region. So they wandering around, stay for a long time, and effectively enhance the conductivity modulation dramatically into this region. So that was a landmark paper just from the calculation and the simulation. Sure enough, a few years later, Toyota, the same company who make a Prius, they came back with a pretty smart way of making a structure with a 300 nanometers critical gap. They do not have a fab with a 300 nanometer or 100 nanometer photolithography capability, but they were able to make this kind of like a bottleneck kind of structure using an older photolithography capability. And sure enough, they're not quite as good as what the Nakagawa predicted, but they're a whole lot better than the state-of-the-art silicon IGBT reported even today. Okay, so this shows a fairly clear direction in silicon IGBT. We're not at the end of the road yet. There's still room for improvement. And the other concept, of course, is something called the superjunction IGBT. We heard about the superjunction power MOSFET, where the CoolMOS and also devices offered by a few other manufacturers. Basically, you do not make a single dimension p-in junction. You make a pin junction with interdigited long skinny fingers. This way the electrical field will get diverted. So for the same doping level for the N's and the P's, you can support 4, 5, 6 times higher breakdown voltage. Same theory can be applied to IGBT, okay? And there's some research work down this road as well. And the other one is, of course, if you switch the semiconductor material from silicon with silicon carbide, you can get a much, much higher breakdown voltage. These are the two devices reported by Cree 2 years ago. 15,000 volts and 12,500 volts IGBTs with extremely low conduction loss. So this is quite amazing. Of course, it's still pretty long way from the actual before we can see some product on the market. So in summary, IGBT is the device of choice for medium power application. But we haven't reached the theoretical limit of the fundamental silicon IGBT structure yet, even after 30 years of a pretty amazing technology advancement. Okay. There's still a lot of the potential and the return for investment in silicon and also in, got it wrong, wide bandgap semiconductor power devices. So there's a potential emerging opportunity to push IGBT into 1 to 100 megawatts high power domain. I think that could be for the application side, that could be the next new frontier. With that, I'm open to questions and discussions.
Can you comment on how strong the correlation is between the evolution of the gate driver circuit with respect to the IGBT technologies? Have they become as simplified in terms of technology? Just to have an idea.
That's very good. You must be scratching your head, busting your head against the wall, doing the gate driver circuit, I guess. That's the same story for the last 30 years, by the way. So you're not the only one who suffer from that. Gate driver technology is extremely critical technology to bring out the full potential of IGBT device performance. In the early days, people pretty much use the power MOSFET driver, just simply borrow it, put it into the IGBT driver. For lower frequency, when you do not care about the efficiency that much, that's a workable plan. But when you push the IGBT to almost to the edge, to the envelope, almost to the bursting point of the device capability, the gate driver circuit is extremely important. Maybe not so much so as the improving the efficiency. There's some correlation between efficiency and that, but mostly just to keep your device from smoking. Really, I mean, if you do not design your gate driver circuit right, you can easily burn the IGBT. The dynamic process is so complicated for the IGBT. Sometimes even your gate driver, you can't fully control that. I know there are a lot of research, not only for the big feedback loop, but there's some, very small feedback loop, especially when you try to put IGBTs in series, in parallel, try to balance the IGBT, make sure it's not a one IGBT stick the head, too early before, 10 nanoseconds before everybody else does, right? Yeah. It's extremely important. It's sometimes it sounds like an art to me. There are only a handful of companies, very few companies doing that. Concept being one, right? There are some other companies, Fuji Electrical, they have their own thing, but it's a lot of high quality work invested into that driver technology. For those of us we're trying to do something in our lab here, we probably can emphasize on 1 or 2 aspects of that. But to come up with a full-scale, good for all kind of a product solution, you're competing with somebody who have $20 million already invested in that technology. So it's hard for our university guys to compete with that.
So you said you're working on wafer level IGBT.
Right.
Could you comment about their I2T ratings compared to the other technologies right now?
Say that again.
Could you compare
R2T?
I2T,
Yeah. You basically bring the thermal factor into the discussion, right? I2T. That's a term people use in the circuit breakers. See, when we talk about you potentially if the IGBT device technology having further advances, you can have a 5 times higher current rating. Those are without the consideration of I2T kind of a thermal constraint. Yes, at a certain point, if you still use the old packaging technology, we're going to run into the limit of the I2T. The good news about the wafer scale of the IGBT is the wafer is sandwiched about 2 very large, very heavy copper pieces. So you get heat extracted from both sides. Not only just the current, but also the heat flow extracted from both sides. And those copper plates, they also serve not only as a heat spreader, but also serve as thermal capacitors in case of a huge transient. Sometimes we need a good thermal capacitor to handle those large power, load transient. So I would imagine that with the sandwiched structure, we still have a lot of space to move forward. Yeah, Robert.
You provided a vision here for pushing IGBT, sort of encroaching on thyristor technology and sort of higher voltage,
Right.
high power.
Right.
In particular, you mentioned sort of the superjunction devices, right? The IGBT is also getting pushed from the bottom, from the CoolMOS technology.
Yes. Yes.
What do you see being the 600, 1200 volts?
Yeah.
Are they being pushed out of that segment by superjunction devices?
I think with the pricing of a 600 volts, well, they typically do the 650 volts of CoolMOS now. As the price of those products, they used to be very expensive. Now, good performance, better performance than 600 volts IGBT because they can switch faster with the same conduction, same current capability, but the switch loss is much lower. The advantage IGBT has is low cost. A smaller die size, it's a cheaper fabrication process compared to the CoolMOS process. But with the price on the CoolMOS keep coming down, I think that market will be eroded by CoolMOS for a lot of those, at least the high performance segment. Okay. Low performance segment, nobody cares. IGBT is still cheaper, but the high performance segment, 650 volts, PFC design, and some of the fractional horsepower motor drive. I think what you said is absolutely true. The CoolMOS will push into that market. For 1200 volts, it's very difficult. The way people are making those CoolMOS devices to get a low-cost fabrication process is still pretty far away. So I think IGBT will hold its place in the 1200 volts application, but 600 volts, it's anybody's guess. Yeah.
Any more questions for our speaker? Well, let's thank our speaker now.